It's time once again for StoryCorps, a project that records Americans talking about their lives. Today we hear the story of 31-year-old Julio Diaz. He's a social worker from the Bronx.
So I normally tell a joke at this time, but I'm going to do something a little different, and hopefully you can hear it. But I'm going to play this for you instead. It's in lieu of my humor. You get something different.
In New York City. And he has a daily routine. Every night he ends his hour-long subway commute to the Bronx one stop early, just so he can eat at his favorite diner. But one night last month, as Mr. Diaz stepped off the train and onto a nearly empty platform, his evening took an unexpected turn.
So I get off the train, I'm walking towards the stairs, and this young teenager pulls out a knife. He wants my money, so I just gave him my wallet and told him, here you go. He starts to leave, and as he's walking away, I'm like, hey, wait a minute, you forgot something. If you're going to be robbing people for the rest of the night, you might as well take my coat to keep you warm. So, he's looking at me like, what's going on here, and he asks me, well, why are you doing this? And I'm like, well, I don't know, man, if you're willing to risk your freedom for a few dollars, then I guess you must really need the money. I mean, all I wanted to do was go get dinner, and if you really want to join me, hey, you're more than welcome. So I'm like, look, you can follow me if you want. I just felt maybe he really needs help. So, we go into the diner where I normally eat. We sit down in the booth, and the manager comes by, the dishwashers come by, the waiters come by to say hi, So the kid was like, man, but you know everybody here. Do you own this place? I'm like, no, I just eat here a lot. He's like, but you're even nice to the dishwasher. I'm like, well, haven't you been taught you should be nice to everybody? So he's like, yeah, but I didn't think people actually behave that way. So I just asked him in the end, I'm like, what is it that you want out of life? He just had almost a sad face. Either he couldn't answer me or he didn't want to. The bill came, and I look at him and I'm like, look, I guess you're going to have to pay for this bill because you have my money and I can't pay for this. So if you give me my wallet back, I'll gladly treat you. He didn't even think about it. He's like, yeah, okay, here you go. So I got my wallet back. And I gave him $20 for it. I figure maybe it'll help him, I don't know. And when I gave him the $20, I asked him to give me something in return, which was his knife. And he gave it to me. It's funny because when I told my mom about what happened, no mom wants to hear this, but with her, she...
All right. Okay, so, that was in lieu of a joke. I have your attention now, right? Okay, so, yeah, so I stole that story off of a talk I went to by a Berkeley grad. I think it's Vipin Mehta. He started an organization called Giftism. Look it up. It's interesting. Okay, so we're going to talk about graphs today. Yeah, I love graphs. Okay, yeah, I love graphs. I love the rain. I'm from Seattle. It's a happy day. Okay, so you guys should get perked up because I really, it's really good stuff, and we need the rain anyway because when the rain comes, the hills turn really green. That's, the rest of the year, the California is the golden state, meaning it's brown and dead, right? It looks, the hills, so it'll be nice. So here's some color. So what this is a map, okay? This is triangle world. Okay, so there's the red country, the purple country, the blue country, and the green country. And now what we want to do is we want to make sure to color these countries in different colors, right? So these are the borders. And in this picture they are, red, green, blue, and purple. And one way to sort of represent this problem is a graph. So we make a vertex or node for each country. So there's the red node, the green node, the blue node, and the purple node, okay? And then what we want to do is we want to say that two countries that are next to each other are not colored the same color. Because if we color the green triangle and the red triangle both with green, it would be hard to tell the difference. It would be hard to tell which country was which, right? In a map, this is sort of the normal thing. You're given this diagram, and you want to color in the diagram so that all the adjacent countries are different colors. So the way we represent that is we put edges between countries that are adjacent. So the red country is adjacent to the purple country, and it's adjacent to the green country. And the green country is adjacent to all 3 other countries. The purple country is adjacent to all 3 other countries. And the blue country is adjacent to the green country and the purple country. Right? Okay, so one thing you want to do in general is maybe, we're computer scientists. So the question is, here's a problem. What does Christos always say? Can we do better? So what's even the definition of better here? What might be a definition of better here? How might we color this in a better way? Yeah, so because I was safe to ask that question here because we're all computer scientists in an art class, they would say, well, so it looks prettier, but that's not. Here we just know it's fewer colors, right? Okay, so can we do this one with fewer colors? Okay, so how do we do that? Yeah, so it's a slightly subtle algorithm. Every one of those, you can't change any of the colors, right? You can't change any one of the colors by itself and get fewer colors. But you can actually. Oh, there you go. Okay, so that's fewer colors. Okay, so there you go. Right? Because the red and the blue weren't touching each other. Okay, so the problem here, you can think of it as a map color, or you just think of this graph. And this graph is telling you which countries are next to each other. And what you want in the graph problem is that no 2 vertices that are connected by an edge, no edge, for every edge, the endpoints should be colored differently. Right? Okay, so this is called the coloring problem. So let's add a node. Okay, so now it's gone from triangle world to triangle and blobs. Okay. So we can add this new red country is adjacent to both the purple and this lower left triangle and this upper right triangle, upper left triangle. Okay, so and you can represent that adjacency with a graph. So we could color that one purple, right? We've originally colored it red, but again we can do this with. Can we do this? So the red, that's 4 colors. So let's do it with 3 colors, which we can do because this new country is not adjacent. This vertex, it's easier already to use a graph. This vertex is not adjacent to this vertex, so they could have the same color. Okay, now I have another country, and again, I'll represent it with a graph. It's adjacent to those 3 countries, and or actually 4, I guess. 1, 2, 3, 4. All 4 of those countries. So now there's 4 colors here, and the question is, can you do better than 4? You see these 4 countries? If you just look at those 4 countries, they all touch each other, right? Since they all touch each other, like, let's just try this. Let's color green. It doesn't matter what we color green, right? We'll just color it green. Now, red needs to be different from green, so it can't be green. Okay, now the blue country can't be red or green, so it must be another 3rd color. And now the red country can't be red, green, or blue, so it must be another color. All my choices were forced, right? So I need at least 4 colors. I had no choice in this matter. Okay, 4 colors are required, and there's a theorem, it's a famous theorem, that for any map, 4 colors is enough. We're not going to prove that theorem. It's just not in the scope of this course. So, okay? So that's a cute little problem. Another way to see this is to view it as, let's schedule our exams. And let's see, we have these 5 classes, and what we're going to do is draw lines between them if we think they should not be scheduled at the same time. Okay? So, for example, 61A and 70, a lot of people take both of those courses, so we should not schedule their final exam at the same time, right? And 61B and 61C, after 61A, you can kind of take either, so that's fine. 61B and 70, yeah, maybe you can take that at the same time. That seems reasonable. 61C and 70, sure, why not? 170, after you take 70, you're welcome to take 170, but you should have taken 70 and 61A before 170. So they can be, you know. So while these guys, you can take them at the same time, so you shouldn't have the exams at the same time. Whereas 70 and 170, they don't conflict. Nobody should be taking both of those. Okay, so they can be scheduled at the same time, right? So let's color this so that we can color this in this fashion, these two. Okay, so I colored it in 3 colors. There's green, blue, and purple. And for every edge, you know, this edge is green on one side, purple on the other side. This edge is blue on one side, purple on the other side, right? So every edge is multicolored, right? Okay, so now you can put all the purple ones in one slot, all the blue ones in one slot, and all the green ones in one slot. Okay? And so what you've ensured that people who are taking the same course don't have to be in the same final slot. Right? Does this make sense? So it's another graph coloring problem, right? Okay, so graphs, I love graphs. Look at that. Isn't that pretty? So this graph is telling you the heritage of Unix. I don't know whether you've heard of this operating system. It's called Unix. When you log into those machines that you really hate and submit your homework, that's on Unix. Okay, so your Macs, they're also on Unix. They're actually a Unix operating system for your information. They just hide it from you. But this is the heritage of this, and so it just tells you where it came from. So you get, it's kind of like a tree, except you have jump edges across, right? From here, this came back in and influenced this particular type of Unix. So Berkeley figured heavily. There's this thing called Berkeley BSD Unix. That's actually was developed here at Berkeley, and it's a fascinating history. You should look it up, and it's actually what the Mac is using underneath. Okay, so this is a chemical network. You may use a graph to tell you the relationships between what chemicals sort of influence the production of other chemicals. Okay, and I'll show you a cute demo here. And okay, so this is a graph. This is a link graph. Okay. Okay, so what it's going to do is going to tell you it's going to hkn.berkeley.edu, and then it's crawling, and then it's going to represent each web page as a node in the graph. Okay. Okay, now show me the graph. Okay, maybe. Please, baby, please, baby, please. The processing? Oh, man. Oh, bummer. No, it's okay. Isn't it okay? Did I do it wrong? Oh, bummer. Oh, bummer. Okay. Are you sure? Okay, well, that makes sense. Okay, let's try this again. Dot. It better be worth it after all this, huh? Oh, yeah. It keeps going, right? The internet's like this. This is crawling a little bitty piece of the internet, right? So it's sort of doing what it does. Yeah. Some other things get bigger, yeah. So I'm going to kill the applet. You guys want to see another one, or? All right. Google doesn't have any links on it. It doesn't do anything. Oh. Did I do it right? Okay. Okay, now show me the graph. So the one thing is this one should show you connections between descendant web pages. It doesn't, but it somehow it's a little weak. But all in good time. So it'll go for a while, obviously. Okay. It's pretty cool, right? So anyway, graphs are really fun. There's lots of things that you do with them. They represent anything. Yeah.
What do these colors represent?
I don't know. I tried to click on them. They don't. So I guess it seems to limit itself, right? It seems to be limiting itself somehow. So. Yeah. Is there a legend at the bottom? All right. Okay. Well, that's really not the point. So let me. I love it, but. Okay. Okay. So what was I doing? F5. Okay. Link graph. Show demo. Okay. So graphs are cool, right? So let's see how to work with graphs. Okay. Here's a graph. It's kind of related to the coloring graph we had before, but I just renamed it. So often. In our book and in class today, after this one, we're going to use letters for the nodes. But in general, I wanted to use numbers here because, in a computer, we really are using integers to index various things. And so you would typically name the nodes 0 through, this is a 6-node graph, 0 through 5. And you might have a matrix that tells you whether something is connected. So if you look up an entry 1, 0, it tells you that node 1, is connected to node 0, right? This is 1, 0. Okay, it says these two are connected. On the other hand, 1, 1, okay, well, that's itself. 1 is connected to everything. That's not a good example. Let's look at 2. 0, 1, 2. So it's a row indexed by 2. It's not connected to 4. Okay, so this matrix isn't right. Okay. So, but you put a 0 if the edge is not there, and you put a 1 if it is. Okay, so I think I made a mistake on row 2. So let's go on to something I didn't make a mistake on. So there's another. So in general, what we want to say for a graph is we denote the vertices as a set, and the set is V. You call it V in general. That's just what we're going to do. And in this case, the graph's vertices are 0 through 5. And you also have a set of edges. Here you have 0, 1, 0, 2, 0, 5, 1, 3. These are all pairs of vertices. Yeah. Yeah, I think I messed up. I can't figure out matrix representation. We're never going to use it again. Please. I hate it. Okay, I'll fix it on the slide before I post it. Okay. But yeah, I just made a mistake when I filled out the matrix. So okay, so now the edges, these are very important, the V and the E. Okay, so the V is something we're always going to use for graphs to represent the vertices. And the E is a set of edges. Okay, so it's just pairs of vertices that are connected. Okay, and this is the representation that we normally use or we think of because it's a bit more efficient for algorithms. And we're gonna look at these two representations and see how they compare. So here, node 0 is connected to 1, 2, and 5. Node 1 is connected to 0, 2, 4, and 5. Node 2 is connected to 0, 1, and 3. Right? These things you can implement with the list, and this whole graph is essentially an array of lists. Right? So given 3, you can tell who it's connected to by just unindexing this array. Okay? So now what are the basic operations you want to do with the graph data structure? You want to see if there's an edge between U and V. Okay, now in the matrix representation, that's easy. You just look up the row U and the column V, and you see if there's a 1 there. Okay? And if it was a correct matrix, that represents some graph, maybe not this one, but it tells you whether there's an edge there. And that's fast on a computer. It's order 1, right? You're just looking up one location in an array. Okay, on the other hand, for the adjacency list, if you want to check whether 1 is connected to 5, you have to look at 1, and then you need to scan over the adjacency list. So it might be a little bit more expensive to do, to say whether 2 nodes are connected using the adjacency list representation. So that's this number. And it's written in blue because, you know, it should be written in red because it's worse than the matrix. But in fact, I wrote it in blue because in fact, by using a hash table, you can make this be O of 1 as well. But for all practical purposes, for most algorithms, it's really, this is, for the algorithms we use in this class, this is not the sort of the interesting thing. The interesting thing is this one. These other two are more interesting. Okay, so now, another thing you want to do is get the neighbors, all the neighbors of U. So if I want to get all the neighbors of 2, what do I need to do? I just need to return this list, right? And it's whatever the length of this list is. And that's what this D is, the number of neighbors of U. Okay, that's the complexity of the neighbors operation. Okay? And now, what about the final frontier here, space, right? Okay. The problem is, when I tell a joke, I just distract myself, and it's not even funny. So, okay, so V squared is the total space here, because the matrix is a V by V matrix. So the total number of entries there is V squared. Yeah.
Why did you say that the adjacency list of LUV is O of magnitude V, but neighbors of U is O of D?
O of D, yeah, I could have said O of D here too, yeah. But in the worst case, it's O of V.
Yeah, but you didn't say the worst.
Yeah, you're right. I should have said this is O of V in the worst case too. I mean, but in this case, it's really good. There's something better about this particular thing. Here, the answer you're looking for is a yes or no, right? Here, you're actually looking for a list and the list is that long. So in some sense, this is perfect, right? I'm giving you something in the time it tells you to look at the answer. So this is perfect. This is really, it should be O of D, but in the worst case, it could be way worse than what you would like, right? Because the answer you're looking for is just, are these two connected? Are these two guys your friends? And then you have to look through all of their friends. So, yeah, it's not as bad as O of V, but in fact, I don't even think this is an issue because mostly we're not going to use this particular operation. And second of all, with the hash table, it's an exercise to figure out how to do this in O of 1 average time. Okay, so then this neighbors of D, this is sort of the adjacency list, sort of pre-processes and just has it in the order you need. Just hand back it's an array lookup. Okay, now the space is V squared for a matrix. Here, the total size of all your adjacency list is just a number of edges. Okay, plus the number of nodes, right? You actually may have a node that has no edges next to it, but that's sort of a degenerate case. Okay? Okay, so this is sort of the basic data structure. This is one we're generally going to use, and you know, it's pretty efficient. This data structure is linear in the size of the input, essentially, and it gives back adjacency lists quickly. Okay? Okay, so now, there's this guy, Theseus. Theseus was some sort of ancient hero. He had to kill a minotaur. I gotta, you know, did you guys ever see this commercial about Dunkin' Donuts? I gotta make the donuts. Okay, well, anyway, he got up one morning and said, "Oh, I gotta kill a minotaur today. You know, you guys just have to go to class. He has to do this." So, and he has to do it in the maze. It's even worse than that. There's the daughter of the king who was making him do this, Ariadne. Says, "Oh, this guy's cute." Okay. Now, fortunately, she's pretty smart. Okay, so she gives Theseus a ball of thread and some chalk. Okay. Okay. So why does he? So now what she gave him is an algorithm. Okay. She said, "Explore a room." So she's going to try to help him find the minotaur. What's the problem with the maze? Is you just wander around and wander around. You can't escape. You can't. You know, you're lost forever in the maze, right? This is the problem with the maze. So Ariadne, you know, she doesn't need to talk much because she's, you know, telecommunicate or whatever. So she gives him this ball of thread and this chalk as tools to be able to navigate this maze. How do you know whether you've been somewhere before? What would you use to tell you you've been somewhere before? What would you use to be able to get out? Right. Right? So the ball of thread is the ball of thread. What is the ball of thread really? It's a stack, right? Clearly, the ball of thread is a stack. You unwind it and you wind it, right? Okay, and the chalk is, you know, you could change the memory location, right? You can store some data. Okay, so now Theseus was, when he wants to explore a room, what's the first thing he does? He marks the room, puts a big X on it. And now for each exit, he looks through the exit and sees the next room. If it's marked, he doesn't go there. He's already been there, right? Okay, so then he looks at the next exit from the room, and so on. If it's unmarked, he goes in the room, he unwinds the thread, right? The thread is there, so he unwinds it. And then he explores from that room. And what does exploring from that room do? Well, he uses recursion, right? He goes back and explores the room. Right? Yeah. 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 Good question. Okay, so he's asking what's the point in the chalk. For undirected networks, you can, but how do you know you've been there? You forget. You forget what the room looks like, right? They all look the same. How do you know you've been there? Yeah, right? Isn't that like here? Like I go here, okay, and I want to go this way. Does that make sense? Okay, so and then I've already been there. And if I go there again, what happens? Oh, this is what would have happened to Theseus if Ariadne wasn't there, right? No good, right? It's good I have chalk. So, okay, so wine. And now how does he go back? So when he went in the room, he wound the thread. Once he's done, once he's gone through all the exits for each exit, then he's back here, right? He's already looked at all the exits. And then he winds the thread to figure out where he came from. And then he explores the next exit in that room. Okay? Okay, so this is, yeah, so he was a computer programmer. So let's see what he was doing. Wait, searching. Okay, well, that slide didn't have much on it. So this is the algorithm rewritten. Okay, we set the visited for each vertex to be, that should be, when you explore a vertex, what you do is you mark it with chalk. That's setting the visited to be true, right? And then for each edge that comes out of this, for each edge coming from this node, for each edge VW, an edge from V to somewhere, you check W. You say, is it marked by chalk? Okay, that's not visited. Has it been marked by chalk? And then if it's not visited, you go explore it. Okay? So the chalk we see, it's these visited marks. Okay, where's the stack? I mean, where's the thread? The thread is a stack. Okay, the thread is a stack. Is that okay? The thread is a stack. That was supposed to be a surprise, but it's not much of a surprise. Okay, is that clear? So the algorithm that ancient Greeks, again, they invented everything. Okay, so let's run the algorithm. So we're going to start from A. What we're going to try to do is see what's reachable from A. Right? This is the entrance to the maze. Yeah. The vertices. Yeah. We're marking the rooms. We marked Theseus marked a big red or big chalk mark in the middle of the room, saying I've been here. Yeah. So he's worried about the order of the edge. When you return from explore, you need to. How do you know you're? What if Theseus does this? Yeah, he's right. I mean, there is a problem with Theseus. It's not much of a problem for computers, but it happens to be a problem for Theseus. What he's saying is there's some room, and there's some entrances, exits, right? And so Theseus goes in this room, and it finds a dead end. He marks the room. He comes back. Now, then he goes out this room, and that's a dead end. Then he comes back. Why doesn't he go look in this room again? Right? So Theseus maybe should mark the entrance, but we don't need to do that because our loop remembers. Oh, sorry. Okay, our loop remembers, right? For each edge, he just goes in order maybe the exits are numbered, okay? One thing you could also do is go to the next one. You could always just go clockwise. When you come back out of the room, you go along the right-hand side. Maybe. Well, that's fine. He just goes over and then comes back, right? Because he sees that it's chalked, right? Okay, so now let's just watch Theseus in this one. So what he does is he goes over the edge there. He goes to there, right? So from A, he picks one of his edges to go out, and he goes to F. From F, he goes to C. From C, he goes to D. From D, he sees that F is already marked, right? Because we've visited the one true on F. So he goes back. Then he sort of goes backwards. He's going backwards. That's unshading it. Okay, and then he goes to F, and then from F, he already explored C. Now he's back at F. So he has to go over some edge, the next edge in his list, and the next edge in his list goes to G. Okay? And then he goes back to F, goes to A, goes to B, goes to E, has nowhere to go from E, comes back to B, comes back to A. He's all done. Okay? He's explored the whole graph. Okay? So now I colored the edges red, or the edges he walked on. These are called tree edges. The explorer builds a tree. Okay? So when you say what's the edge you call this subroutine on? So for one of these edges, you called this explorer. You actually went down there. You checked whether the other one was marked, and you went down there. And that's a particular type of edge, and that's called a tree edge. Okay? And the other edge is the blue edge. He looked at DF. He looked at this edge DF, and then he said, okay, I don't need to go across it because F has already been explored. So I just go back. That's called a back edge because it's going back to one of my ancestors. Okay? Okay, so these are just definitions that we're going to use sort of throughout. Okay? Okay, so so the correctness, we want to say every node that's reachable from A, this algorithm finds a path, finds every node that's reachable from A. Okay? Yeah. Yeah, it means there's a cycle, right? Why does it mean there's a cycle? Right. I mean, it's a back edge. It's a little bit subtle as to why it's a cycle, but there is definitely a back edge means a cycle because let me tell you, for undirected graphs, whenever you see an edge of this form, it's going back to an ancestor in the tree. And because it's going to an ancestor in the tree, there's a path through the tree to you, and then there's an edge back to the ancestor, which creates a cycle. Okay, so now I have to argue that all edges that are not tree edges are back edges. They do go to an ancestor. Okay? Okay. So, I mean, they're undirected, so to and from are a little bit, it's the direction in which we're exploring it is the way I'm directing it. Okay? Okay, so this is the algorithm. So what I want to prove is all and only nodes reachable from A are reached by Explorer. So I started a node A, and I want to say I reach every node that has a path from A to it. Okay? Well, when U is visited, the stack contains node on a path from A to U. That's what the stack contains, right? So how did you get here? Well, somebody explored an edge. He may have done other things, but he came back and he explored another one, and then he explored another one, and he explored another one. All these nodes on this path, if you look at this path here, A to F to C to D, when D is first discovered, this path, A to F to C, A, F, and C are all on the stack, right? Let's see. Right? What does the stack contain? It contains A. What's it contain now? It contains F. What's it contain now? A, F, C. What's it contain now? Right? So the stack contains a path. Okay? So so when it's visited, there's a path from A to V. You can't get there without following a path to it. Okay, the harder case, if a node is reachable, you need to prove there's a path, you need to prove this algorithm finds it. So first of all, if a node is reachable, what that means is there's a path from A to U. Okay? So there's a sequence of edges that that connect A to U. So it looks like that. So there's some edge, some edge, some edge, some edge. There's some Z, some W, some edge, some edge, some edge. Okay? Okay, so now let's the reason I picked out Z is, well, if all the edges along this path, all the nodes are reached by the algorithm, we're done. Because that would mean U is reached. So we go back to along this path, and we find the first node that's not reached. Okay? So A is definitely reached. So this one's reached, U is not reached. So this one's not reached, 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 not reached, reached, not reached, but they have to hit each other, right? There has to be a node where this one is reached and this one's not reached, right? Okay, so Z is explored, W is not, right? Okay, well then that's clearly this can't happen. Why is that? What would explore if Z do? Well, it would explore W, right? Since explore of Z would explore W, then W can't not be reached. Okay? So that's a contradiction. This pair of statements can't be true, because if Z is reached, then W will also be reached, because that's the way the algorithm is coded. Okay? Okay, so that's kind of a slick proof, but what do we really do there? That's an inductive proof. Do people recognize this as an inductive proof? Okay, so one way to prove, so the property, it's an inductive property that we wanted to prove. Every node with a path of length k or less is reached. Now that's an inductive statement because it has an integer in it, right? It has k in it. Okay? And you want to prove this property is true for every k. Okay, so this is really the same. So one way to prove it is, let's prove it for k equals 1, and then prove it if k equals 1, k equals k implies p of k plus 1, right? That's the way we did it in 70. Here we did induction, but we also did this way in 70. You can do an induction by sort of contradiction. So you say, well, if this property does not hold, there's some k where the property doesn't hold. There's some value k, which in this case is whatever the length of this path is, right? Where it doesn't hold. But if you say there's some k where it doesn't hold, then you say, oh, well, in fact, well, this one, because for this k, this is the smallest k where it doesn't hold, w. So we know if w is the smallest k where it doesn't hold, there must be a predecessor, z, whose distance to A is less than k. And the property does hold there. Because the property holds there, we know that w must actually be reached by the explore process. So there's no smallest k where it fails. So one way to prove something inductively is to say it never fails. Okay? And the way you prove it never fails is you assume it does fail, and you show that's ridiculous. It doesn't fail. Right? That's what a contradiction is. You show something's ridiculous. Okay, yeah. Yeah. Yeah, so the size of the graphs are integers. Yeah. I mean, my natural numbers, in fact. Right? At least only in this class. Please don't ask me about infinite real numbered graphs. Yeah. I mean, so it must hold for every k, and then Joe is done. Okay? So if there's no smallest place where it failed, if it can never fail, it must always hold. And then we're done. Okay? Okay, so now let's look at the running time. Okay, how to analyze this? Okay, this is the recursive procedure, right? It's explore, and what's it doing? It's calling explore, right? It's recursive, right? So we should write a recurrence, right? Okay, first of all, just to make the recurrence easy, I'm going to let n equal the size of v, the number of vertices in v, and m be the number of edges in E. Now I'm going to write a recurrence. And then I'm going to write this, I guess, I don't know, right? Because is there an n minus 1? The explorer it's not really working on a smaller problem, is it? I mean, what is the notion of progress? Because not only do we call it, how many times do we even call it? Actually, do we call it d times this? Oh my. Okay. So I don't know how to go with the recursive thing. It's a recursively phrased algorithm, but it's not, you can't really use a recurrence for it. So you don't use recurrences in graph algorithms. Okay? How do we do something else? You charge work to something. That's the way we're going to analyze this. We're going to charge the work to some object, some notion of progress. Are we making progress? Anybody have any idea whether we're making progress? What's the progress in Explore? What does it do as it goes? Yeah. Yeah, it marks a node. It marks a node when it enters it, right? Explore marks the node when it enters it. Okay? So why does it mark the node? Why am I here? I don't know. But why does it mark the node? Okay, well, we see in Explore here, if not visited. So for any node, how many times can Explore be called? Once, right? That's the purpose of marking. Okay, so now we know, like, let's look in this particular little thing. So Explore is only marked once, okay? So for node X, you only explore it once. Okay, so you can't do the same work on this node over and over and over again. Like I tell my kids, over and over. Anyway, you don't do that here, which is really good, right? And so, yeah. Yeah, but you don't call Explore. You do check the visited again. That's true, but you don't call Explore. Okay. So now, when you do Explore, what do you do? When you explore a node, what do? You process each incident edge. So I'm just calling this loop processing, step 2. It says for each edge, do something. Okay? And what is that something? It either checks whether the other end is visited. If it's visited, it's not much work at all. It does not, it just checks, right? It does 1 unit of work to check the other end for a visit mark. On the other hand, it might explore. But then we're not going to worry about that work because we're going to charge for that to that vertex, right? That vertex is charged for the work we do in that recursive call, okay? Or the local vertex, okay? So really for each node, the work we could charge to this node is just basically he's explored once, and each time he's explored, he processes each incident edge. So now for each edge, now that's still not so easy to see, right? Because how many incident edges can one guy have? It could have order v. It could have a lot of edges. So this could be n squared, order n squared. But in fact, if you think about it a little bit more carefully, let's charge it to the edge. This processing of the edge, I'm going to charge it to the edge. I'm going to say, oh, the work I did on you on this edge, you're responsible for it, you edge. Okay? So that's what I'm doing. I'm this work in this loop, I'm not counting it, I'm not doing anything other than saying, okay, well, the edge is responsible for this work. Okay? The node is responsible for the visited, step 1. But the work in the loop, I'm assigning it to each edge that's being worked on in the loop. Seems reasonable. You charge the client, right? Okay, so each edge processed, and now each edge is only processed twice. Why is it processed only twice? Either one end or the other end. And now that's your answer, right? When you process, you can either process it as a tree edge or as a back edge. Okay? So each edge is processed twice, so the total running time is O of n called to explore the node, that's the visited, the step 1 up there, and O of m to process the edges overall. Now this is weird, right? Edges are being processed right and left. It's going on like this, but we know this, we just say, okay, well this edge, how often do we look at this edge? Twice. Total work, order m. Okay? Yeah. It could be. It could be, yeah. So if it is a square, then it's a big problem. So this is one question, is what is the size of the problem? Is it the number of vertices? Is it the number of edges? Well, here, the complexity of describing the problem is the number of vertices plus the number of edges. Okay, so this is linear in the total size of the description. Like for example, if you draw a map, if I take a graph and it's, like your friend's graph, like you take the graph of all your friends, you're not connected to everybody, right? I mean, maybe you are, but I'm not, okay? You only have a few hundred at most, most people have around a few hundred. They don't have a few billion, right? There's a billion in the graph. So the size of the Facebook connection graph is not a billion squared, it's a billion times 100. Okay, so it's much smaller. So the number of edges is a billion times 100. So this is a much better answer than n squared for real examples. Okay? Okay, and then there's something down here. So you add them up, right, to get the total time. Okay, so now, we just we love our explore routine, but I should give you a break. So I'll go have a break for a minute, and then we'll go on for. Okay. So all right. So just to get your attention, this is a joke that psychologists use to measure why people laugh. Okay. So you might think it's not funny, but here it goes. Okay. So there are these two muffins in an oven, and one of them says, "Boy, it's hot in here." Okay, so never mind. All right. Okay. I'll tell you the rest at the end of class. All right. That way you won't sleep through the end. Anyway, so. Okay. Oh, no. Okay, so let's see. Okay, so process the whole graph. What should you do to process the whole graph? We have this great thing, it explores, it builds us this cool thing, which is called a tree. It gives us a tree, which is this red thing that lets us sort of get around the graph. It's really nice. Okay, so what we're going to do is some graphs are not actually, that worked where you got this nice tree if the whole graph was connected. Okay? But maybe you have separate components, right? Maybe the map is of the world and you have the Americas are connected and Europe is connected, and somebody, will call Explore on America and think that's all there is in the world, when in fact there's a larger world, right? So it's important to run it on the whole thing, right? So that's what this one is. So what we're going to do is essentially use this to sort of have a look at the whole world, right? That's what DFS. This is called depth first search. You've seen it before, but for each node U, visited of U is false, and then for each node U, if it's not visited, you explore it. Okay, so if you start with the node in America, you'll presumably get the whole the Americas. You'll get the Western Hemisphere here, and you'll have visited that, and then you'll pop out of this loop. Explorer will have visited all of the Americas. Then you'll pop out of this loop, and then you'll say, all of this. Let me explore Mexico, but Mexico has already been explored, so it won't go into the Explorer, right? Okay, and then it'll go, let me explore France, and France has not been explored, so then the Explorer will actually be called in France, and we'll get all of Europe and various things. Okay, so that's what this depth first search does. It just really wraps up Explorer in a loop, so you could kind of get a feeling for what's going on in your whole graph. Okay? So the running time is order V plus E, because for each component, you just think of it as a separate graph. And it's all linear, so you add up all the sizes. Intuitively, you get a tree for each connected component. You get several trees. What are several trees? What do you have when you have a lot of trees? Yeah, okay, good. Okay, so, okay. Oh, okay. So now, that was fine. So now, what we're going to do is we want to now use this as an algorithm. Okay. So I just said, I said let's just do this, and it will sort of give you the connected components, right? Because each separate tree is a connected component. Okay. But let's write it out in a neat format. Let's put it in a neat format and say, what I want when I say compute the connected component is I want to number each guy with their connected component number. Okay? Because output matters, right? You have to put it out in the right format so that people can use it. So when I want to output the connected components, what I'm going to do is I'm going to give out an array, and for each node, I'm going to number it with which component it's in. Okay? Does that make sense? Okay, so we're going to do that by changing Explore. So we're going to add these two procedures called pre-visit and post-visit. Okay, and pre-visit is I'm going to compute this output vector, this connected component number, and I'm going to just set it to the CC number. Oh, pre-visit is right. For each node in V, set CC. This should have a CC. Oops, this is okay. So DFS is a little off here. So let me write it correctly. DFS of G is for each node. Okay. CC equals 0 for each node in V. Okay, for each one of these, if not visited, explore V Okay, so the idea here is that you pick any node in V. In our case, it was America. We picked America, then we explored all the countries in the same connected component. Okay, and that's what this one call to explore would do. And now what pre-visit does is for every one of those countries, it sets their connected component number to 0 because it's initially 0. Okay, and then we pop out, and then we go through another node, Mexico. Mexico has already been explored, right? It's already been visited. So we don't explore it again. Okay? And then we go to France, and then we call explore again. And this time, CC is set to 1. Okay? So France will be labeled with the number 1. France and everything reachable from France will be numbered 1. Okay? So this is a CC number. So each node will be labeled with the connected component number. The runtime is order V. So that one's labeled 0. That's a pre-visit. It's labeled 0. That's labeled 0. That's labeled 0. That we don't do anything because it's already been visited. We go back. That's labeled 0. We go back. Okay. So now we may look at some of these other nodes in this loop, but we don't explore them because they've been marked. That's why they're kind of light blue. These have all been marked as visited. So eventually we get to B, which is actually the next one. So then we explore that one, and that should be numbered 1. Okay, so I got another bug on my side. Okay, so and then it unexplores. Okay, so now we're sort of getting enamored with ourselves. We're being a little narcissistic about the whole thing. We love our algorithm. We just love it. Okay, we love it so much. We want to know everything about it. So the algorithm is going to sort of talk about itself. Right? We're also in California. We understand its pain. And so so we really want to see what it's doing at all times. Every move it takes, every step it takes, we want to record what's happening. We want to record that. Okay? Say when what happened. Okay? So that's what the pre and post is. So the we're going to change these procedures. We have these procedures here. These cool procedures, which are pre-visit and post-visit. For every vertex, we pre-visit. What would Theseus have done? He would mark a big chalk. Okay? What would his post-visit be? Well, he would check if there's a minotaur and kill it. Or the pre-visit would be he would kill the minotaur if he saw it, right? And the post-visit was to mark it with chalk. Okay? So these are just generic procedures that you add to DFS that you could run on each place. And so pre and post here is we're going to set pre to a clock value, and then we're going to increment the clock. Every time we move, we're going to increment the clock. Okay? And post, we're going to increment the clock too, and we set this post number. So we're just computing these numbers. Okay? And this time the DFS code is the appropriate code. Okay? So this is just This is self-referential. It's just trying to see how it behaves. Okay, just for fun. Well, and it's going to be very useful. But let me set up exactly what it's doing. So the clock goes up to something like 2 times the number of tree edges. The first pre is 0, right? Because that's what you start out at. I'm just practicing. Now this is a big property. For any 2 nodes, U and V, this interval. Right? Each node has a pre-number and a post-number. Okay. And this pre-number is talking about time. Every time you call explore, you increment the pre-number. Every time you leave explore, you increment this time, this clock. Every time you go in, you call explore, you increment the clock. Every time you leave the explore, you increment the clock, right? That's what the pre and the post do. They're at the beginning and the end of explore. Okay? So this interval is telling you sort of how long you're exploring. You. Okay, that's what this interval is. It builds you a timeline for your algorithm, and this timeline, this interval in the timeline is how long you're exploring U. Okay, and this interval is how long you're exploring V. And so now one thing about these intervals is now we can prove some properties about this interval, which will let us prove properties about the algorithm eventually and what it does. Okay, so these intervals are either disjoint or one is contained in another. Does everybody see why? Right, okay. So remember, this is how long we're running explore on something, right? This is the time interval we're running explore on something. This is a recursive algorithm, right? This is a recursive implementation of an algorithm. So if we run something for this interval, for any other node, either it's run at the same time, right? We can't call explorers this way, right? We can't call two explorers at the same time and have them overlap in time, right? Because every explorer is from another explorer. Okay, so it must be in that interval. Okay, so that's the interval is a clock interval on stack. Either both are on the stack at the same time. The only way use V's explorer can be the only way V can be explored at the same time as U is U must be on the stack, right? It must have been called eventually by U. So therefore, this one must finish before U's explorer finishes. So it must be inside of that interval. It must be contained in the interval. On the other hand, if they're not on the stack at the same time, these intervals must be disjoint, right? So that's what this property comes from. It's from how I learned to love a stack. Okay, this property comes for that. Okay. Okay, so that says. Okay, so we could do the pre's here. So those are the pre's. We just increment. I mark at 1. I haven't written down the post yet because I write the post when I leave explore. I'm still exploring F, right? Here I'm exploring A, I'm exploring F, I'm in the middle of exploring A, F, and C. There's 3 recursive calls on the stack. There's a recursive call there. I try to look at F. I don't need to go there because it's marked. I go back. Now I've popped D off the stack. I've left its explore. I write down its post number, which is 4. I write down C's post number, which is 5. I then pop up to F. I'm not done with F yet, right? From F, now I still haven't explored one of the edges. It's still black. So then I explore across that edge. I do that one. Pre is 6, post is 7, post is 8, post is 9, start again, 11, post is 12, post is 13. Okay? So now an edge, UV, is a tree edge. Now I'm thinking of these as directed. If V is on the stack when U is on the stack, that's what this is saying. V is on the stack. If V is on the stack when U is on the stack, then V is contained if U by U. The interval of V is contained by the interval of U. Okay? And now this back edge, it's the other way around. Basically, this back edge for D went back here. B is still on the stack, right? So that means that B's interval contains D's interval. Okay? Okay, so that's the 2 possibilities. No edge between U and V if they're disjoint intervals. Okay, so this says if there's a back edge, there's a cycle. That's what he was asking earlier. Okay. Okay, so now, these are just it's largely it's a lot of sort of. I'm going to do this a bit again because these pre and post we don't have a punchline yet, so we'll have a punchline unfortunately next time. But okay, so DFS on a directed graph. So the starting point is the root. B is an ancestor of V, of U. So we just write some terminology for these directed graphs. So now it's directed. So for directed graphs, before we do directed graphs, we're going to do this. So root is a starting point. V is an ancestor of U, so that makes sense, right? If I descend from U, if I'm reached from U by an explorer, by a sequence of explorer calls, then V is an ancestor of U. If a sequence of recursive calls from V reaches U, then V is an ancestor of U. Or it's on the path from V is on the path from or to the root, to you. And descendant is obviously just the inverse relationship. Okay, so let's look at depth first search on the directed graphs. Here something a little bit more interesting happens. Okay, so again, you start with A. Those are the pre-numbers that are going up. So here, you can't go to C because C, the edge is in the wrong direction. Right? We're only allowed to follow out edges here. Okay? So we go across to D. There's a convention in the book that's followed. When we ask you to do a breadth first search, you do it in lexicographic order. Does that make sense? So D is you just assume that things are ranked in order of letter. Okay, so D is the next one on B's list. D then explores C. C looks at B, and it sees that B is marked, right? Okay, so now it pops itself off the stack, and it puts down its post number. It pops itself off the stack, it puts down a post number. Then you're back at B, and B starts exploring G. There's its post number. Okay, so this kind of edge, so first of all, before we go on, like this edge here is a little different, right? It's not quite a back edge. It's kind of, it is a back edge, right? It's sort of going back to one of my ancestors from C to B. It's not a tree edge. The red edges are tree edges. Okay, so back edges is C to B. That's the back edge. Okay. Okay, so now we're exploring down here. A goes to F. F goes to E. Now E is going to explore its outgoing arc. Now E goes to what? What is it going to look at like? But it's not going to explore D because D is already explored. It's marked. Okay? So now I'm coloring that green. Now that's because this is a little bit different type of edge. Is that green edge going to an ancestor in the tree? No. Okay? With undirected graphs, that was, if you took any non-tree edge, it was always going to an ancestor in the tree. Okay, yeah. Yeah. Sorry. I got to switch my letters around, but yeah. Okay, so then there used to not be an arc on the previous. Okay, so I added the arc later. Okay, sorry. My lame excuse. Okay, so Okay, so this one is a different kind of edge. It's not a back edge. It's not going to an ancestor. So life is a little more complicated. Before, you only had tree edges or back edges. So here, if you have a non-tree edge in a directed graph, you have a cycle. Okay? Here you have a non-tree edge. You may or may not have a cycle. Right? Does that make sense? So this green edge is a non-tree edge. And if I delete that blue edge there from C to B, does this graph have a cycle? No. Okay, but the exploration would be exactly the same. So directed as soon as you have a non-tree edge in an undirected graph, there's a cycle. You're done. Okay, you can tell whether it has a cycle. Here, I have a non-tree edge. I don't know yet. Okay. So there's 11. There's 12. And then what does A need to do? It needs to explore this last edge, which I colored purple. Okay. So now these. And then it pops itself off the stack, and everybody's happy. So we have the pre's are in black, the post are in blue. Okay, so a tree or a forward edge, again, the interval for V is contained in the intervals for U. So a forward edge, a tree edge means V is a descendant of U. It means that B was explored while the explorer of U also explored V. Since the explorer of U explored V, that means the interval for V, the time in which it was being explored, that interval of time is inside the interval of time in which U was being explored. Okay? So that's what a tree edge is. And that's what a forward edge is too. And what is it? Do you see a forward edge here? Do you guys see a forward edge here? Anybody see a forward edge? Yeah, this one, A to E, right? A to E, E's interval is 10, 11, which is inside A's interval, which is 12, 13, which is 0, 13, right? A's interval is 0, 13. The pre is 0. The post is 13. Yeah, so 10 to 11 is in 0. It should be 13. Okay? Another way, the way the book writes it is we write the bigger interval like this, and we just put the little interval inside. Okay? This guy's interval, which is E's, is inside of A's. So therefore, this edge, AE, is either a tree or a forward edge. Okay? Now a back edge, that just has the reverse property. The interval of U should be in interval of V. I'll fix that. Okay, so here CB is the interval. So C 3, 4 is in 3, 4 is the head's interval, and that's inside the tail's interval. Okay? So that's what this happens here. And the cross edges they have disjoint intervals, right? In this case, the cross edge is E's interval is 2, 5, and it's completely before 10, 11. Okay? So these are the only possible relationships between these intervals, okay, for edges. Okay, so now we have a way to sort of categorize edges. Okay, so now we're going to use this whole thing to actually see whether graphs are acyclic. Okay, so that's what we want to do, and that's what we'll do next time. Okay, and so you want to know the punchline for this muffin joke? Okay, do you remember the joke? Okay, so there are these two muffins baking in an oven, and one of them yells, "Wow, it's hot in here," and the other muffin replies, "Oh my goodness, a talking muffin."